So I'd like to welcome everybody to this special event. This is the normal time and place for the math department's colloquium, but today we are very fortunate to have a special guest and to be double billed. There is an annual event called the Thomas and Yvonne Williams Fund for the Advancement of Logic and Philosophy, which sponsors special talks once a year at Penn, not necessarily in the math department. And we are very fortunate to have Mr. Williams here he was an undergraduate here and a graduate student in computer science, and has kindly provided, along with his wife, the funds for this. So the event is sponsored jointly by the math department and this fund. This fund is chaired by...
Well, no, I have some welcoming remarks.
All right.
So
I am going to defer to Scott Weinstein, the chair of philosophy, who will do the actual introduction of the science.
Thanks so much, Ron, and thanks so much to colleagues in mathematics for opening the colloquium series to welcome this talk. We are really very, very grateful for this. And on behalf of the School of Arts and Sciences and Penn Engineering, I'm very pleased to welcome you to the third annual Thomas and Yvonne Williams Lecture for the Advancement of Logic and Philosophy. And we are most grateful for the generosity and vision that Tom and Yvonne have shown in establishing the fund that supports this series of lectures and that makes possible other educational activities at the university and at upper schools in our region. It was a great pleasure for me to work with Tom when I first arrived at Penn, and to watch him develop through the study of logic and philosophy that clarity of mind which he has so successfully brought to bear in the sphere of practical affairs, and that sustains his ongoing passion for the life of the mind. And it remains a great pleasure to work with him now on a range of activities that will advance a general appreciation of the power of reason to clarify problems both practical and theoretical. I'm doubly grateful today for the opportunity not only to acknowledge my debt to Tom and the other students I have taught here at Penn, who have so deepened and enlivened my appreciation and understanding of logic and philosophy, but also to acknowledge a debt to a distinguished logician whose extraordinary gifts as expositor and teacher inspired both Tom and myself when we read his lovely book, Saturated Model Theory, in an independent study project in 1977. It is a great honor and pleasure to introduce Gerald Sachs to deliver our third Williams Lecture. Dr. Sachs has made seminal contributions to recursion theory. In the early 1960s, he established fundamental results about the Turing degrees, such as the Sachs density theorem, and introduced new techniques which form the basis for the development of deep insights into the structure of the degrees of unsolvability over the past 4 decades. Dr. Sachs also pioneered the generalization of recursion theory to the study of computations on infinite ordinals and infinite sets. Developments in this area have illuminated the bearing of recursion theory on questions in both set theory and model theory. It is worth noting that several of the leading logicians who contributed to these developments, such as Harvey Friedman, Leo Harrington, Richard Shor, and Theodore Slayman, were among Dr. Sachs's 29 doctoral students, as is our esteemed colleague Nate Ackerman. In recognition of Dr. Sachs's enormous contributions to logic, not only through his own research, but also through the training of an extraordinary group of leaders in the field, the Association for Symbolic Logic established the Sachs Prize for the most outstanding doctoral dissertation in mathematical logic. Please join me in welcoming Gerald Sachs, who will share with us his reflections on Gödel. Thank you.
This may sound like something very rare, a talk delivered after the eulogy. It's a great honor to be here, and I would like to add my thanks to Tom and Yvonne Williams for making this possible. So I think I'd like to take the jacket off. I'll keep the microphone. I'm not a philosopher, although this is something of a philosophical talk. For that reason, and also it's an old habit, I like to begin with disclaimers up front. So I'm not a philosopher, nor was meant to be, but in my next life I think I'll be a philosopher. I think philosophers have more fun. Am I right? There are philosophers here, aren't there? Who's a philosopher? I think they have more fun. And Gödel had a very definite opinion, which I'll eventually tell you about the relative importance of mathematics and philosophy. Okay. So this is not a true philosophical talk. I mean, I will take various positions, but this is really about Gödel. And some stories about him based on personal contact over time. I'm getting to the point now where I'm beginning to be the last link with a number of people, such as Gödel, Tarski, Church. I even met Skolin once, though I can't claim to know him, but I did meet him once at a meeting. So I'll tell some stories about Gödel and try to give you his views on things as I see it. And he had a method for approaching almost any problem that came up in philosophy or math or even in life. So I became aware of it over time. It's also I'd like to point out right at the start, in case I don't get to it, he was a contrarian. His interpretation of his own work always seemed to be the exact opposite of everybody else's. Anyway, he was consistent in that regard. He was also capable of changing his mind. And I'll give an example of that. I know there's a lot of time for questions at the end. We don't have to leave until 6. I'm certainly not going to speak for more than an hour. But also, I'd like to encourage people to break in during the talk. Doesn't have to, could be a question, or you might add something, or correct me on something. Try to start an argument with me. That's my wife laughing. All right. I got to do something with this. Okay. So I think the microphone is working. All right. So I'd like to begin with misunderstandings of the Incompleteness Theorem. Of course, that's not true here, but it is true in the world. You get very bright people like Francis Crick, or Roger Penrose, talking about the Incompleteness Theorem in their books. And they've heard about it, they've read a bit about it, and they all like it. It seems to suit whatever thesis they have about anything at all. So somebody might use it to strengthen the case for quantum mechanics. Well, really, there's no connection. No connection at all. Or somebody might use it to prove the brain is a Turing machine. or someone might use it, which is very widespread. I think a lot of people, because of Gödel, not so much the incompleteness theorem, but what goes on in the incompleteness theorem, the way the proof of it, and the resulting definition of computable function, that the mind is just a machine which computes various computable functions from time to time. And there was even a bunch that used the incompleteness theorem to prove the mind is not a Turing machine. You can, whatever you want to do, you can use the incompleteness theorem. All right. There is a paradoxical aspect to the incompleteness theorem. It's of course historically of immense importance. There's not many theorems in math which will be remembered a couple of hundred years from now, but that's surely one of them. Let me try and state it very simply. In other words, it's a theorem about formal systems. And a lot of the misunderstandings stem from a lack of clarity in the minds of some about what a formal system is. It's a very simple idea, which I won't state. So it's a theorem about formal systems and the limitations of certain formal systems. And fortunately, mathematics is one of those formal systems. It's a theorem about the limitations of mathematical reasoning. It upset a lot of people when it first came out. I knew someone who was there the night the news came to Göttingen, and of course they couldn't go to sleep, and they looked at the proof and so on. And a lot of people were upset. They thought he was doing great damage to mathematics, but I think he made mathematics more interesting. So now when you attack a problem, for all you know, it may be one of the undecidable ones. I mean, some mathematicians I know, in order to avoid trouble, would work on trying to prove a given theorem on Monday, Wednesday, and Friday, and would try to refute it on Tuesday, Thursday, and Saturday. But that's not good enough. It may not be provable, it may not be refutable. So this worried a lot of people. I had a colleague, Raoul Bott, a very famous topologist, who thought that almost everything was undoable, and that it was amazing that anyone ever obtained any result at all in mathematics. So that's an extreme view. I think we, by instinct, tend to look at problems which are doable. Now, Gödel's own view, of course, here he's being a contrarian. His own view, well, first of all, he certainly had views about implications of his work. So I'm the sort of philosopher that believes no mathematical theorem settles any important philosophical problem. Who agrees with that? Only one person. I mean, but it's hard to resist drawing these conclusions. But there's a great gulf between a mathematical result and, a philosophical problem. But Gerald certainly drew conclusions, though never in print. If you look at his papers, he doesn't do that. Even when he's asked to do it, he's very reluctant to do that. And he certainly has theorems about which you could philosophize forever, but he avoids that in print. But not privately. So privately, he didn't even think that the Hilbert program, if you're familiar with it, was erased by his result. He thought the Hilbert program is now, very much alive and even more interesting than it initially was. I don't have time to go into that. He did think, and he never wavered on this, that any problem we come up with, we can solve. It's hard to say exactly what he meant by that, but he's very clear on this. Look, if you've got a math problem, we can do it. We can do it. It may require us, I'll come back to this later, we may need more axioms, we may not have enough axioms. But there is a solution and we can do it. And so if that's the case, it would follow that the human mind is not a Turing machine. No chance. But if it is, there are things it's not going to do. I mean, they're very simple questions, terribly simple, and it's can't do a thing. But he felt that didn't apply to the human mind. And I mean, if he was pressed on this, he seemed to think that we have organs of perception that we don't know a lot about, right? That we don't know the whole story about how about our organs of perception. There's more to it, but he was vague. Okay. So I wanted to say something paradoxical. So the incompleteness theorem will be remembered hundreds of years from now. But from a mathematical point of view, it's more important to look at his so-called completeness theorem. His completeness theorem is mathematically more important. I'm sure many of you are familiar with it. The incompleteness theorem is somewhat of a dead end. It stimulated a lot of work in recursion theory and so on, but take a very long view, it's a dead end. It's negative, right? It says, gee, you can't do this, you can't do that. Who wants to hear that sort of thing? But the completeness theorem, is very powerful. And year after year, there are surprises which are drawn from it. It's a positive thing. It gives you the ability to create new mathematical structures using very, very weak hypotheses. And it is, in fact, a universal method. Any mathematical structure that came to you by any means whatsoever could have been created by an application of the completeness theorem. So that suggests that it's very powerful, and it is. And it's the fundamental theorem of a subject called model theory, which, as the years pass, turns out to have applications to many other areas of mathematics. For example, it led to Abraham Robinson's theory of infinitesimals, which Gödel thought was one of the great achievements of modern logic. Not everyone agreed with him, but Gerald thought other people had attempted to give a rational account of infinitesimals, but they all failed. And it was important that Robinson had finally succeeded. Well, it comes, yes, please.
Hi. Would it be possible to quickly state the completeness theorem?
Completeness theorem says, I have a first order language, there's a lot of those. I have a set of sentences from that language. I'm told that the set of sentences is logically consistent. In other words, you cannot derive a contradiction from them using just the rules and axioms of first order logic. That's a very strong, that's a very weak assumption, because practically anything is consistent. All right, so then that set of sentences has a model, has a structure, which you could build in a very direct way, say in the style of Henkin, which is a model of all those sentences. The power of it really resides in the fact that usually the set of sentences is infinite. If it's finite, you're not saying much. You're still saying something. It's still, I mean, in Gödel's original proof, he just does one sentence. Here's a sentence that's consistent. Here's how you make a model of it. That proof, his actual proof, has some interesting features which I don't have time to go into. Okay, so I see in my notes, I want to mention his proof of the completeness theorem was intuitionistically correct, which is historically very interesting. He thought, I mean, privately, he thought the intuitionists were doing nonsense, but still they had to be taken seriously. They attacked him very severely. I mean, he didn't reply in kind. In particular, they Well, they essentially attacked the Incompleteness Theorem. They attacked the Completeness Theorem. They attacked the Hilbert program. They were very, very contrary people back in those days. Okay, so next I'd like to raise a very important philosophical question. Did Gödel have a sense of humor? I think this is important. And it's related to a short paper, the only philosophical paper I've ever published. It's in an obscure place. And it studies the following question. Is there an effective method for computing the difference or determining the difference between a serious philosophical statement and a parody of a serious philosophical statement? I guess my position was, but I wasn't firm, that there was no way to tell the difference. I think that's one of the attractions of philosophy over math. In philosophy, there's endless room for humor. Although there are not many humorous philosophers, but there are some. I mean, in Quine there are jokes, are there not? Here and there are jokes. They're deliberate. Yeah. He doesn't. No.
Well, no. There are papers written in this very light style. So, like, by Quine, like his paper on natural kinds is like Maxwell Smart. It's like, would you believe a kind is a similarity set? Would you believe a similarity set is a kind?
Okay. All right. Yeah. So he was a humorous philosopher, but not in class. In class, he didn't really like questions. You had to submit a question in writing, and then he would answer it at the next class. So you got a very good answer. I mean, nothing off the cuff. All right. So did he have a sense of humor? So I'll let you judge. The following episode occurred. Once I asked him, how about monads? Because I knew he had a very... But for him, the great philosopher was Leibniz. I said, how about monads? They're unaware of each other. Right? I said, I find this theory very strange, that the universe is composed of monads who have no information about each other. Right? They're called windowless monads. And it seems to contradict common sense, because we look around and we see an immense harmony. Everything seems to be working out pretty well. And Leibniz's answer was that God imposed this harmony. So I asked him what he thought. So he said Leibniz was wrong. Everything that happens, he says, it's obvious. Everything that happens affects everything else. I mean, this is part of science. And he says, furthermore, Leibniz was wrong about everything. Then he pauses and he says, but it's just as hard to be wrong about everything as it is to be right about everything. Now, he didn't crack a smile, but I thought that was a very amusing remark. So I thought, well, he cracked a joke. Or did he? Or did he? I thought about that for a long time. I should have tested it more. I should have cracked jokes in his presence from time to time, but I guess I was intimidated. I did try some little bit of wit occasionally, and there was a hint of a smile. So I tend to think he had a sense of humor. But I'm not sure to this day. In his posthumous writings, I don't see any sign of humor. So related to this question is his zest for life. He did have a zest for life. He was like a little boy, really. He was full of wonder an excitement over various developments in logic, math, philosophy. I mean, as if he were a very bright 11, 12-year-old. And that never went away. So that suggests maybe he had a sense of humor. Let me give a sort of example. I guess he doesn't count as an important philosopher because of his lack of publication and also his total rejection of positivism, of analytic philosophy, and all that other stuff that happened mainly in the 20th century. So he's a throwback, and hence he's rejected. But he is a philosopher. So there was this dinner once at the Institute for Advanced Study in Princeton. And I was in Princeton that year, so the director asked me to sort of take care of him. I would sit next to him at dinner, and that is Gödel, and keep him out of trouble and so on. On the other side of him, he had an old friend, Oscar Morgenstern. So we spoke during the dinner, and of course, I was always eager to hear whatever he had to say. And he brought up, I don't know why, he brought up one of his favorite concepts, the absolute, with a capital A. That's not a concept that 20th century philosophers tend to bring up, the absolute. So what was it to him? In my mind, it was the class of all sets, but maybe it was something more for him, I'm not sure. But he seemed to be talking about the class of all sets, hence of all mathematical objects. So that's worthy of being called the absolute. And he says, and he told me, and he seemed to have this boyish enthusiasm. He says, language does not enable us to define the absolute. Right? If you had a formula, f of x, it can never happen that that formula has exactly one x that satisfies it, that x being the absolute. That can't happen. Because we know from the reflection principle in set theory, if I have a formula f of x and f of v holds where v is the class of all sets, then f must also hold for some set. In other words, anything you say about the class of all sets, which is true, is also true for some particular set. And hence, you can't define the absolute. And he said, and then his eyes lit up. He said, isn't that wonderful? We know something important about the absolute just by logic, just by reason. And he was full of enthusiasm. I noticed something else at that dinner party. His sense of courtesy, an extremely courteous man. He wasted, I thought, too much time with crackpots. You could call up and make an appointment to speak with him. And of course, he, as you might imagine, he attracted a lot of crackpots. He was usually protected from them, but not always. But anyhow, at this dinner party, which was given by the director of the Institute, the director left before it was over. And Gödel was very puzzled about this. He kept asking me, why is the director left? Should not all the guests leave before the host leaves? I said yes. I pretended to be puzzled, but I wasn't. So was he a mathematician or a philosopher? Well, he was both. Back in the 60s, there were some young Turks in logic who didn't think he was that good a mathematician. But of course he was. He started as a graduate student in group theory. Somehow he became a student of Karnak, and his thesis was the Completeness Theorem I mentioned earlier, a pretty good thesis. although it was not appreciated, I think I don't think Karnak understood it, or what it meant, or what its implications were. But it was certainly accepted as a good thesis. Even people like Hilbert and von Neumann, I think, didn't fully absorb it. But so he could do mathematics when he wanted to. And there's some very, I mean, he didn't write many papers, but there are some very ingenious arguments there, for that time. And in fact, one of the things I want to do at the end of the talk is talk about the one I like the most. He valued philosophy more than mathematics. He thought philosophy was a higher subject. In fact, there's a hierarchy of subjects, and philosophy was above that. So, do the philosophers here agree? Yes, don't be afraid. And I have concrete proof.
We're outnumbered.
I have concrete proof. The library at the Institute in Princeton is divided roughly into two parts. So it's like two libraries, and there's a big room in between where you can just sit around and pretend to think deep thoughts. But so there are the two sections. So one is reserved for the science, mainly the physical sciences, and the other for humanities. So after he arrived, he asked the librarian to move the Journal of Symbolic Logic from the science side to the philosophical side, because he felt it deserved to be there. So philosophy was higher up in his esteem than math. He had strong feelings about the way mathematics was to be written. Namely, it should be easy to read a mathematical proof. Right? You should be able to pick up mathematics and just read it. You might not understand it fully, but you should be able to follow it and see that it was correct with very little pain. Well, this is certainly not the case in the real world. And so he thought it was just a matter of finding the right definitions. He's not talking about making clever, intuitive remarks, but just if you have the right definitions, it's easy to follow. And I think his Continuum monograph is a good example of this. It is easy to follow line by line. It gets a little dense near the end, but still, line by line, there's no big surprise. There's not much chance of understanding it on a first reading, because there's a lot going on. But that's okay. That comes later, and at different times to different people. And he felt very strongly about that. And I think this was related to his Platonism. There's a connection I sometimes think I see between his Platonism, his optimism, and his contrariness. Right? So it's very optimistic to think that we can solve any problem we come up with. Despite the Incompleteness Theorem, despite all the undecidability results, so-called. That's certainly a very optimistic view. I've already mentioned his contrariness, and in particular his contrary interpretations of his own work. So I'll go right on. In his posthumous papers, volume 5, he has a proof of the existence of God. It's a little sketchy. But it was not an idle exercise. It was a proof, I think, being developed by someone who believed in the existence of God. But not just because he read some authority on the subject, but he had come to that conclusion. So how do you give a proof? Well, I won't go into the proof. It's kind of mathematical. I think the most important element is a maximal principle that he uses. I mean, it's not quite the same as Zorn's lemma, or the existence of maximal ideals in rings, but it is a maximal principle. And that might be the mathematician's choice to be the centerpiece and a proof of the existence of God. Though I know some of you might be thinking, well, the maximal ideal is not unique, but he's got that covered because he's made some slight changes. In other words, his God is not only exists, but is also unique. So different people have given different accounts of this proof. So be warned. There are elements of modal logic in it, or there appear to be. Some people leave that out. So he brings in necessity and possibility and uses them in an important way. So no time to go into that. Let me say a bit. I was hoping for more objections, but maybe I'll save it. His view, his proof of the existence of God is a typical example of his method, what is his method? So you have an important question, mathematical or philosophical or theological. How do you settle it? Well, what you do is you whip up some axioms that are relevant and which you hope will be sufficient to settle the matter by means of pure deduction. So where do the axioms come from? Well, they come from our ability to perceive certain fundamental truths. We can simply see that certain statements are true. So this is related to his Platonism. I'm not going to defend it. But he doesn't say self-evident or anything like that. They're true because you see that they're true. In other words, the light of reason is very powerful. So you can see that certain things are true. But you can't settle everything that way, only the fundamental things. So you've got these axioms, and then once you've got them, because you never know if you have enough, but once you've got them, then you try to deduce what you're trying to show is true. So that's how he dealt with the existence of God. He first gives you some axioms. Let's see, what's one of the axioms? If I have two good qualities, A and B, then their conjunction is a good quality. So he's thinking of God, his God, as I think the infinite conjunction of all good qualities. He's getting ready, so he starts with a very modest axiom, which no one's a challenge. So this axiomatic approach, possibly he learned from Hilbert. He certainly pushed it very hard, brought it into mathematics. And this is his method, and he's prepared with this method to attack any problem. Now, there's a problem that has obsessed him, I would say, for most of his adult life, the continuum problem. So for him, the continuum problem is a real problem. The answer is either yes or no. Let me remind you of what the continuum problem is. The continuum is the set of all real numbers, if you like. So it's a kind of formless, it's like the ocean, right? Here are all the real numbers, and there's not much shape or form. Of course, you can impose all kinds of structure, but in its pure state, it has no structure. So the question is, how big is it? So we know from Cantor that it's bigger than the integers. It's uncountable. So there it is. It's big, and here are the integers. Is there anything in between? Is there any size in between? So one way of putting it is to say, if I take an uncountable subset of the real numbers, you can put it into one-to-one correspondence with the set of all real numbers. That's one formulation. So he worried about this. He wanted an answer. So there's an expository paper by him in long ago, in the, I think it's in the American Mathematical Monthly. The title is "What is the Continuum Problem?" And he discusses it. And he comes to the conclusion at the end of his discussion that the continuum hypothesis is false. In other words, it does not represent the smallest uncountable card. And he gives a lot of reasons for it, but they all have the same form. If you believe the continuum hypothesis, then you can, in the style of real analysis, construct something weird. In other words, it leads to unappealing examples of all kinds of things in analysis. That seems to be the main reason I think it's false. So the evidence, in other words, there are all these existing structures you can attach to the real numbers, and then they don't work out as nicely as you might like if you believe the continuum hypothesis. All right, so the continuum hypothesis is false. Well, if it's false, what is the size of the continuum? Yeah, I never understood why he worried about that. If you think the continuum hypothesis is false, why not simply look for a proof that it's false? But I don't think he did that. He looked for a proof that tells you what size it is. So he chose olive 2. He seemed to think olive 2 was right. So he didn't seem to have any reason that I could think that I knew about for choosing olive 2. So he used his method. Over the years, he would occasionally develop a set of axioms about the real numbers and try to use them to prove that the size of the continuum is olive 2. And once in a while, he thought he could do it, and even circulated these attempts, but they always had a hole in them, and he always withdrew them. So this went on and on and on. Finally, in 1975, he startled me one day by saying, I think the continuum hypothesis is true. It's true. I said, what? I said, you've changed your mind. He said, yes. I said, you wrote this expository paper. You said it was false. So he looked at me and he said, I was misled. So he blamed that on all those classical analysts that he talked to. Right? They thought it must be false. Gave you too much power to construct too many weird examples. And then he stuck with olive 1 for the rest of his life. But he stuck to his method, axioms that would prove it equal to olive 1. This was pretty tough, though. Of course, it's almost obvious, I hope at this point, he didn't think his own work, or the later work of Paul Kohn and others using forcing, he didn't think any of that shed any light on the truth value of the continuum hypothesis. It didn't tell you anything at all. I took that to mean he didn't think mathematics could solve an important philosophical problem like the continuum hypothesis. But his approach, what I'm calling here his approach to solving problems, certainly sounds mathematical, but maybe axiomatic is a better description. Okay. One day, to be nice to me, he finally came up with an answer to my question, what are the important open problems in logic? So again, this is around 1975, though it's still a good list. So I've condensed it. So the first problem he mentioned was the consistency of analysis. He felt the consistency of, say, number theory, that is, the piano axioms for number theory with a little bit more. He felt that system had been shown to be consistent. Some people might disagree, right? You recall his so-called second theorem is corollary to his incompleteness theorem, demolished the Hilbert program, and in the minds of many said you couldn't give a useful consistency proof for any of these mathematical systems. He disagreed, and he felt that a number of people had given perfectly good consistency proofs of formal number theory. Perfectly good. One was due to Jensen and so on. So the objection raised by the second theorem was that, of course, any such consistency proof had to use a method that could not be formalized in the system. So Jensen's proof, for example, Jensen's proof of the consistency of number theory is by a certain transfinite induction. Now, this transfinite induction, this particular one, cannot be carried out inside formal number theory. It just misses. In other words, it has a length called epsilon 0, so it's a transfinite induction through the ordinals less than epsilon 0. If you look at any shorter induction, you can't carry it out in number theory, right? So that sort of nails it. And also, of great importance to Gödel was Jensens' argument is clear. You can see what's going on, right? It's clear as a bell. Though Andre Weiss near that, it kind of annoyed me. He said you're proving the consistency of ordinary induction on the integers by means of a transfinite induction. But he had a habit of sneering at almost everything. Then Gödel gave a proof, one of his very rare papers in the 50s of the consistency of number theory, which is extremely interesting philosophically. So here's number theory. Over here is a system he invented. He deliberately made for a moment. So you got a way of and it's a system of computation. So over here, he shows you can transform a proof of a contradiction into a computation of 0 equals 1. You're done. All right. Well, it's a system of computation which, again, after a while is fairly clear, but it has some strange twists. It involves objects of finite type. So numbers have type 0, and a function from numbers to numbers is type 1, and so on. So he has to look at functions of finite type, but they're computable. They're computable. And the notion of computation involving them is, finitary and clear. And I think that's the most convincing consistency proof of them all, the number theory. Anyhow, he regarded that as done. So he wanted something similar for analysis, but that still hasn't been done. There's a formal system of analysis invented by von Neumann, which I won't discuss. But at that time, I was ignorant of the complexity of such a proof. In other words, if you try to look at the ordinals involved, it takes all day just to give a description of them. In other words, using arcane systems of notation. I mean, it's awful. And I did hear some lectures 10 years ago in England by someone who had made some progress along these lines. And he had an idea for doing the whole thing, though it was a staggering enterprise, and he still hasn't done it. But I think it might be doable. Anyway, that was the number one problem. It makes sense. I mean, much of math is just analysis. And it's about time to nail down a consistency proof. Oh, then another one your computer people will love. It's a problem in complexity theory. It was intuitively obvious to him that some computable functions are more complicated than others, more complex. So how about a hierarchy for the computable functions? Where is it? Forget about polynomials and so on, or exponential functions. Where's the hierarchy for the computable functions? A lot of people tried very hard and failed, And I think there are mathematical reasons for thinking there is no such hierarchy. But I don't mean there's a proof, but I think there's evidence against this. In other words, it could be a deep result about the computable functions that there is no hierarchy of complexity. And it's simply not appropriate. And then, of course, he brought up the continuum hypothesis. He brought up P different from entity. It came to light not too many years ago that he was really the first to draw attention to that problem, P not equal to entity. And he did so in a letter to John von Neumann, who was on his deathbed. And I noticed over the years that Gödel's way of cheering up a dying person was to send him a logical or mathematical puzzle. Well, as good as any. Because von Neumann certainly responded by saying, this is a very interesting problem. And he was hoping he would get a chance to think about it. He sometimes went further. There's a letter to Abraham Robinson, who's on his deathbed. And he says, among other things, he says, I don't know your opinion, but I've always thought it ridiculous to view the ego, that is the cell, as a mere assemblage of protein molecules. So that was actually comforting, I think. Okay. All right, so I've come now to my very last point, which is the bit of mathematics which he did, which I find the most beautiful. In his proof of the consistency of the continuum hypothesis, he shows that it's true essentially in a model of set theory called L. L is the class of all constructible sets. So I remember reading it as a graduate student in his orange booklet, and not really understanding it. It seemed too much like magic. In other words, he's got this universe of real numbers, and right at the start, he sort of lays out a lot of real numbers using countable ordinals to construct them. But then he goes on and constructs millions of all kinds of sets, the whole universe of sets, a model of set theory. So he's got to show that maybe way out here you made a new real number that you didn't get down here among the countable ordinals. He takes that real number and he looks at how it was constructed. And he builds what we would now call a countable Skull. In other words, he does something like a downward Skolem-Lovenheim argument. Does that ring a bell here? Yeah. And so he takes that whole, and it's just a countable collection of sets, the new real, the magic real that he's worried about, and some other sets, some of which are uncountable. But there's only countably many items there, and he mushes it down. He shows that it's isomorphic to a certain transitive set. He flattens it out. And then what he's got is an initial segment of his L, and it only has countable height. The real number has retained its value, and so it was constructible down its uncountable level. It's wonderful. So this was not explained clearly in any book or paper for many years. I mean, he did this in the 30s. There's some interesting stories about that, but there's no time. So in the 60s, Harold Kopp and Ronald Johnson wrote a paper in which they gave it a name, the condensation theorem, very descriptive. And it's the main idea in the study of L. So with the passing of time, Jensens did some very, very deep work on the internal structure of L, but that's still the main weapon. And I've always been fascinated and tried with limited success to to use it on some fundamental problems in model theory. But that's another story. So I think that's his most intriguing mathematical work. I still think the completeness theorem is the most important result. And I'll conclude by saying there is deep work now on the continuum hypothesis. It's a bit technical. It's due to someone named Woodin, W-O-O-D-I-N. And the value he gets as a theorem, of course, under certain assumptions, all right, new axioms you might call them, his value for the continuum is alpha 2. So that's consistent at least with Gödel's original opinion. And Woodin gets his result as part of a huge body of work. So there is a book about that thick which gives you the proof. If you're interested. I'm interested, but I'm not going to live long enough to. In fact, if I was born last week, I wouldn't live long enough to read that book. But it's all there. And there might be 2 or 3 people who have gotten through it. Students of his. I've noticed his students all look sort of tired and old before they're very, very tired. So it's, I would recommend being a student of his. But that's, I don't know if that work could be lost, because there don't seem to be people who are ready to absorb it and carry on. So he is actually trying to settle problems in set theory by a method that can be traced back to Gerald. Thank you. Yes, I'd be happy to. I'm disappointed that no one started an argument. Yes. Not too late.
Can you say something about his relationship with Einstein?
Well, Einstein had already died by the time I appeared. So I can say something, but it's all secondhand.
All right.
They hit it off, as you know, very well. Each one liked the way the other one spoke German. And I think Gödel, to be nice to Einstein, even wrote a paper on relativity, as you know, in which the space-time turns out to be finite, which is kind of interesting. So that would have consequences. And he thought that might be an explanation for ghosts. In other words, they were sort of traces of a previous revolution of all of space-time. I don't think he was kidding. I don't think he was kidding. But there's stories about them which I won't repeat. I think they're hackneyed by now, but they got along very well. They went on walks and they discussed everything, not just math and physics, but philosophy, because Einstein had philosophical interests, very strong. And Einstein felt Gödel was not appreciated. The Institute was very slow to make him a professor. That's really scandalous when you think about it. They didn't understand what he did, and the mathematicians did. So Einstein and also von Neumann saw to it that he was appreciated. And von Neumann whipped up a medal called the Einstein Medal, which is still awarded once in a long while, but the first recipient was Gerald. Yes?
So this is half a question, half a comment on the previous comment. So I was very interested in what you said about the absolute was Gödel was very worried about this, because in Carnap's autobiography he says that Einstein was really worried about the problem of being with a capital B. And Karnak, in his modest way, says he set Einstein straight about this. There is no problem, as you, Professor Einstein, have shown yourself. So was this, is this a rejection of Karnak on Gödel's part, or did he? Did Karnak not really set Einstein?
I never heard him say anything approving about any 20th century philosopher.
including his teacher.
He was always very respectful and courteous, but for him, philosophy is back there with Hegel, Leibniz, Kant, Aristotle, Plato. I mean, that was philosophy for him. I mean, he knew all these people. He knew all the people in the Vienna Circle, but he didn't believe a word they said. He rejected the circle totally. I mean, analytic philosophy made no sense to him. Absolutely. To him, it was dehumanizing. I mean, he couldn't bear listening to it. There's a story about him and Wittgenstein, you may have heard, which I owe to Juliet Floyd, a Wittgenstein scholar. They're corresponding about the Incompleteness Theorem, which Wittgenstein could not ignore. In fact, before Church's thesis, he tried to find a decision procedure before Church's theorem, he tried to find a decision procedure for first order logic and so on. So he had reason to be upset about what Gödel had done. So they corresponded, and Gödel was very annoyed with things that Wittgenstein said. And he wrote in another letter to a third party, he says, either Wittgenstein does not understand the Incompleteness Theorem, or he is pretending not to understand it. That was within the bounds of courtesy, I think. I don't think he was pretending. I don't think he understood it. That was my thesis advice as opinion, J.B. Rosser. By the way, I owe my access to Gödel completely to Rosser. Rosser strengthened the Incompleteness Theorem. Gerald had assumed something called omega consistency, and Rosser showed simple logical consistency was enough. So he thought very highly, Gerald thought very highly of that result. So that essentially, since I was Rosser's pupil, I then had access. Yes?
I've always thought everybody had some sense of humor. So how do you define a person with no sense of humor?
Well, it seems to me, I have encountered people who had no sense of humor. In other words, the joke is told, and they don't get it. And whatever the joke is, they don't get it. There are people like that. There's certainly people who don't get it if you explain some mathematical matter to them. And so math is like humor. It's possible not to get it. It's as if they have no need for humor. Most of us take refuge in humor. Well, life is very difficult without humor, but some people don't gain anything from humor. I think they occasionally pretend to smile, just to be very good. Yeah. Yes.
I was going to ask you about what in the world made Gödel go into physics, but since you've already discussed that, let me try another one. I naively thought that Paul Cohen had proved the independence of the continuum hypothesis. So what are people doing trying to compute the ordinal if it's independent?
Well, it's independent. It's really a joint result of Gödel and Cohen that the axioms of ZFC, call it set theory, don't prove or don't refute the continuum. Neither one. I mean, it's open. So, no, Gödel himself suggested additional axioms that would help decide the continuum hypothesis one way or the other. And so someone like Wooden has succeeded. Is the first one really to succeed in this program, in a non-trivial way. In other words, when I was preparing this talk, I thought I would sketch Wooden's argument, but I wisely decided against it. All right. So, I did say in the talk that Gödel felt that his own work and Kuhn's work don't tell you anything at all about the continuum hypothesis. They just tell you that the axioms of ZFC. Now, the axioms of set theory are really very weak if you take a hard look at them. Because suppose I remove one axiom, the axiom of infinity. I mean, it's a big one, right? But it essentially gives us the integers as a set. So suppose I delete that axiom. So what's left holds for the hereditarily finite sets. So set theory, the axioms of set theory are simply the obvious axioms for the finite sets, plus one more, that there exists an infinite set. Well, that sounds kind of a very weak attempt at set theory, very weak. I mean, it cries out for more axioms. And he suggested many of them, but it turned out that most of them have no effect on the continuum hypothesis, though that requires some pain. Yes?
Do you know, did he hear about axiom of determinacy in the big head from the
Yes, I had an unfortunate experience. I guess once again I didn't want to be aggressive with him, but I tried to tell him about the axiom of determinateness because I knew he was interested in descriptive set theory, which he thought was neglected. He complained what happened to further developments in descriptive set theory. So I said, well, there is a lot going on in descriptive set theory yet. They make some use of the axiom of determinateness. He didn't want to hear any more. Why? Because that contradicts the axiom of choice. The axiom of choice is obviously true. You look over there into the real world of sets, and you see for yourself it's true. So, and he almost sneered, though he never really did sneer. He said something like, I suppose it's interesting to see what a man can do with one hand tied behind his back. In other words, he's a man who does not use the axiom of choice. So I realized, I mean, that doesn't really sum up the situation at all, but I just wasn't going to force it, down his throat. Yeah. I mean, they have extended, I think. I mean, they make very limited use of the axiom of determinateness. They don't use the full axiom. And they have extended, in a very reasonable way, classical descriptive set. Yes?
So I'm actually, this builds on the last question nicely. I'm kind of curious about, I don't know, worked out theory, but sort of what this intuitive grasp of axioms sort of was for him. If you could say a little bit more, only because...
Well, it's the real world of sets. There is a real world of sets. So if you want to test some mathematical principle, you simply go there and take a look. If it's a fundamental principle, you should be able to see whether it's true or false.
Right. We'll take the axiom that you gave the example of from his proof of the existence of God. That if two different predicates or so forth were positive and their conjunction was also positive, well, that just seems false. False or either kind of meaningless, because take a game where a really aggressive strategy will win, so that's good, or a really defensive strategy will win, and that's good, but middle of the road is just going to lose every time. Well, does a conjunction mean both? Does it, if they rule each other, if the two strategies rule each other out, then talking about the goodness of a conjunction is meaningless? So
yeah, I would tend to agree, but there is a vagueness here as to what counts as a positive quality. But I agree that that's a difficult axiom to justify. You would have to speak at length about what is meant by positive quality. I guess he was thinking like you're virtuous and you sing on key. The conjunction of those two is certainly positive. Yes.
Of course, we had a question about Gödel and Einstein, and most people know how Einstein felt from an early part of his famous period, the end of his life, about difficulties in quantum theory. And modern physics. And I wondered whether Gödel, with his wide-ranging intellect, ever had any feelings that you know about modern physics.
No, I never discussed physics with him. My guess is he preferred relativity because of his classical orientation. He liked continuity. He liked definiteness. So I would guess he sympathized with Einstein's objections. You know, God does not prove probabilities are not a way to sum up the world. So that would be my guess. Yeah.
Is it easy to give an example of, say, an axiom that you can add to set theory that is helpful in pinning down the cardinality of the continuum, for instance, like, so I can judge how plausible I think it is?
It's not a simple matter.
So they're not just like easy to state.
No, it's a whole assemblage of ideas. Essentially, I mean, I'll speak for 60 seconds if you like. So we look at L of R. R is the continuum. L of R is the universe you construct from the continuum. Assume determinist holds there. So this sits inside the class of all sets, which is much bigger. So then certain large cardinals are assumed to exist in the universe of all sets, and they give you a connection between L of R and V. And it's a very strong connection. You can build up a chain of sort of intermediate inner models. In other words, you can build your way from L of R to V. And since you're building your way, that limits what's in V. So that limits the new reals you're going, or the new sets that you might get. Anyway, it limits V severely. And that sort of suggests that you're going to get a bound on the continuum, that the continuum is not going to be all of 99, but fairly low. But then on the other hand, there's still a lot of power there. The constructions are powerful, so there's still a lot of reals floating around. So you get more than the original all of one many reals. So that's about 60 seconds worth. So it's not just one action that does it, but it's a whole.
And
it's a whole theory.
You have to reject the axiom.
What?
And in particular, you have to reject the axiom.
No, you only reject it in L of R. It's still true
right.
in V. See, that's the beauty of it. You haven't lost anything. Well, you appear not to have lost anything obvious from V. V looks like as rich and strange as it might possibly be. Of course, it isn't. You've killed some of it in a very subtle way. So you're only using the axiom choice only fails in L of R, because that's the only place that determinant holds, just in this little sliver of the universe. That's what I wanted to tell him, but I never got to it.
Is that Wooden's approach, or is that Gödel's approach?
Now, this is Wooden's approach. But I think ultimately, I mean, all this sort of thing is inspired by Gödel's work on Neumann. It's also inspired by work of Jensen. Yes?
I have a question for the philosophers and logicians and mathematicians. So one of the important points, again, to what means sense of humor? You said at the beginning, our brains are not Turing machines. Now, is there a way to define, to axiomatize, okay, so this is sense of humor? What must have a system in order to say,
Well, I don't know. A joke, I think, is something, it's analogous, it's tickling of the intellect. I mean, you can tickle the skin, but you can also tickle the intellect itself by certain kind of verbal constructions, situations, mental pictures, unexpected juxtapositions. I mean, people have written about it.
I mean, this is, the humor always happens in a natural language, not in a formal language.
No. I hesitate to say that.
But it can't be divorced from consciousness.
Has something to do with consciousness?
Yeah.
Self-awareness.
Right. And answering the question about humor is going to be easier, I suspect, than answering about consciousness. Not much easier. And no one's gotten close on consciousness.
Yeah.
They thought a lot more about it.
So consciousness is a kind of awful predicament that we're in. And humor helps relieve the situation. I mean, cats and dogs don't have senses of humor, do they?
You're assuming they're not coming.
Okay, I think this is the last question. The last question.
What were his thoughts on the Crackpots?
What?
What were his thoughts on the Crackpots?
He never commented on it in my presence, but I'm confident in saying that he would reject it too.
Well, let's thank the
And so that way, that's fully consistent. This is what we're talking about analogy for short logic. These are very, very common steps. And forces, the forces that we say, like force, so he has that book. He has, I think, okay, article explaining the idea. So it's really good because you have here semantics if you're not the same, you're not.
But you know, by the way,
they're really cool stuff. It's one of the coolest things that might be going on. He's in programming now. Yes. Yeah, he's working on it for a while. I don't know the actual current course at the moment. I have a friend who's actually working with him.
And they couldn't think of anything else. I can't think of anything.
Or you can make anything because not only you can just consistently regular carbon besides. You can't have it be like alpha. There's more than that. You know that. Yeah.
At that time, you know,
it can be aleph 7, aleph 10, aleph omega, a billion plus 1, aleph omega sub 1, aleph omega sub 3. There's more. You can even make it. You can make it sort of you can be any aleph with one finality, but the aleph does not count.
No, so yeah, you know,
So it can't be aleph omega, it can't be the aleph like 2 omega, anything like that. But it can be aleph 2 omega plus 1.
But the idea is there's an important.
Yeah, it can't be aleph 2 omega, but it can be aleph 2 omega plus 1. That's not going to be
reproducible proof.
You have to want to do something that we're it's really cool stuff.
All right, yeah,
I don't know if you're going to have just one rule. Okay, I'll be here for those who also. So if you send me an email,
then in fact the set has go for 24 hours. And the only known proof requires classification.
Yeah, well, if I make a list of things like that.
This is disturbing.
Good to see you, Mark. To make sure. Take you up to Andre's office.
I was talking about the book